At MMI. Let's start. This is my presentation outline. I will be talking about the methodology that I have used in this experiment, and all detailed results will be at the end of the slideshow. Okay. As described in one of the recent famous image enhancement papers, Zero Reference Deep Curve Estimation for Low Light Image Enhancements by Go et al., many photos are often captured under suboptimal lighting conditions due to the inevitable environmental and/or technical constraints. This includes inadequate and unbalanced lighting conditions in the environment, incorrect placement of the objects against extreme backlight, and underexposure during image capturing. Such low light photos suffer from compromised aesthetic quality and unsatisfactory transmission of information. As is seen from the example, there are lots of good examples of low light image enhancement methods using neural networks in modern studies. In modern studies, the described problem is solved by deep learning methodologies. In the methods, they generally propose a deep network for low light image enhancements. It can be trained end-to-end with zero reference images. This is achieved by formulating the low light image enhancement task as an image-specific curve estimation problem and devising a set of differentiable non-reference losses. The previous figures on the previous slides, those guys, demonstrate the superiority of the methods. Let's look at them again. You can see the raw images, and these other three examples are taken from some recent papers. For classical image processing methodology, the main idea behind the scenes is to shape the histogram of the image, play with constructs, and increase dynamic range in the image. In the project, I would like to achieve such an image enhancement problem with classical image processing algorithms with simple methods and algorithms. And now we are seeing some example photos that I have used in the experiment. In this study, I have used almost same idea proposed in fast efficient algorithm for enhancement of low light video by Dong et al. The algorithm that I have used in the study works by first inverting an input low lighting image and then applying an optimized image dehaze algorithm on the inverted image. In the original study, to facilitate faster computation, temporal correlation between subsequent frames are utilized to expedite the calculation of key algorithm parameters. By the help of this technique, they had an excellent enhancement results and up to 4 times speed up as compared with the frame-wise enhancement algorithms. Applying these algorithms onto single image or single frame will result in still excellent results, but we will not be able to see the speed up at this point because we are working on single frames or images. As defined in the Wikipedia, the haze, traditional and atmospheric phenomena in which dust, smoke, and other dry particles obscure the clarity of the sky. Just by inverting the images, we are also having an image, um, that has a haze problem actually. When you invert this image, you will see something like the symmetric of this image with respect to the y-axis. So they are handling this low light enhancement problem with dehazing the inverted image actually. In the original paper, they propose a novel, simple, and effective enhancement algorithm for low lighting video. They showed that after inverting the low lighting video frame, the pixels in the sky and distance background regions of the inverted video always have high instances in all color channels, but those of non-sky regions have low intensities in at least one color channel. Similar to case of video captured in hazy weather conditions, therefore they applied state-of-the-art image dehazing algorithms to the inverted video frames and show that the combination of inverting low lighting videos and applying dehazing on them is an effective algorithm for enhancing low lighting videos. To facilitate faster implementation, they further utilized temporal correlation between subsequent video frames for the estimation of key algorithm parameters, resulting in more faster algorithm as compared with the conventional frame-by-frame approach. In today's technology, it's very clear think that low lighting image enhancement is much in common with the image haze removal, because after inverting the image low lighting images, the result image look very much like videos occurred in hazy lighting conditions. Figures provide some examples of low lighting images, inverted low lighting images, and images occurred in hazy lighting conditions. In hazy conditions, the intensities of background pixels are always high in color in all color channels, but the intensities of the main objects, for example, houses, vehicles, and people, are usually low in at least one channel because of the color, shadow, etc. When we look at the left part of the image, we are seeing at the top the low lighting examples, middle invert after the top ones, and the bottom one are haze examples. So we are seeing that these two guys have something in common, and we can handle the problem with the same methodology. When we are look at these guys, at the A channel, we are seeing a low lighting video input. At the B part, inverted result from the input image. At the C part, marked image pixel with low intensity in at least one color. At the D part, the haze output, and the E part, final output after inverting the image. Examples of the enhancement results of the proposed methods are shown in the figures. The original low lighting video inputs exhibits very little scene information due to the low illumination level. The enhanced results are shown in B parts, and the red arrow points to the areas with notable enhancements. In figure B, the improvement in visibility is obvious, including 4 vehicles in the background and the license plates of the vehicle in the foreground. More enhancement results are shown in the other figures. From the upper figures, we can conclude that low light enhancement can also be solved and handled as the haze problem, and the proposed methods works very well. During the experiment, I have used different color spaces, different dehazing algorithms, and different histogram shaping techniques. It was all empirical, and some methods works better than the other. They are discussed in the conclusion part. The code will be available with the zip file. If it's necessary to give a receipt for any trial that I have used during the experiment, I have converted the RGB to LAB color space. I have taken the complement of the image, means I inverted it, in order to make it more like a hazed image. After that, I have applied an dehazing algorithm in order to suppress white regions of the images towards the histogram centers. After these things, we can apply either denoising or contrast enhancing algorithm or just invert the image again. Depending on the image, we can apply also saturation enhancement on the image to sharpen the small details. Now we are seeing a successful example of the experiment. Due to the time efficiency, I will be sharing all successful and unsuccessful trials at the end of the video. I have applied all aforementioned techniques to all photos. You can find detailed results at the end of the video. I think you will be shocked just by looking at the just by looking at the experiment results. You will see the power of the classical image processing algorithms. In this study, I have implemented the video-based novel, fast and efficient video enhancement algorithm for low lighting video to the images from scratch. Based on the observation that inverted low lighting images are similar with haze images, I have changed the dehazing algorithm properly and applied it on the inverted images before inverting the dehazed image again to produce out the enhanced low light image. As a drawback of the dehazing method, the methods can lose some details or get over-enhanced because of poor adaptability of the dark channel. In low light conditions, as an experimental result, dehazing image and contrast enhancing on its way better results in any other methods that I have applied on images. As discussed in the introduction part, consumer-grade cameras become increasingly widely deployed. The problem of image enhancement for low lighting images has also become increasingly acute. This is because although camera and video surveillance systems are expected to work in all lighting and weather conditions, the majority of these cameras are not designed for low lighting, and therefore the resulted poor capture quality of renders the video frames unusable for critical applications. To handle such a problem, a good approach is investigated and implemented from scratch. It performs very well on single images. In total, it was a good practice to see the application of theories clearly stated on image processing algorithms course content. These are my references during the experiments. Thank you for your time and patience. Now time to examine the experiment result.